Thank you, Jörg, and thank the organizers for inviting me. It's really great to be here. And I'm sorry I missed that first part, but I was a bit ill. But don't worry, I'm better, and I don't have corona nor monkeypox. But I want to talk today about something that I like to call fake insulators. And when you hear the word fake, probably many of you think about this guy. But I promise this has nothing to do with political issues, fake insulators. It has something to do with a topic that actually Antoine talked a lot about, namely metal insulator transitions. And indeed, I do not advise to try it with a socket to try to find the difference between a metal and an insulator. Just leave that to theorists, because there's a very clear distinction between a metal and an insulator, at least at zero temperature. Because at there's a laser here. Yeah. So at zero temperature, you know that, well, what is an insulator? It's something that actually absolutely has zero conductivity or infinite resistivity. And you know from an insulator that once you raise the temperature a bit, there's usually a gap. So the amount of resistivity that you'll get follows this activated behavior, where delta here is the insulating gap of the system. And as a result, even if you don't really see this activated behavior, you can always say, well, an insulator is something where the temperature derivative of resistivity is negative. Heat it, it becomes less resistive. And on the other hand, we have metals. So of course, those are systems with very low resistivity, but at zero temperature, the difference between a metal and insulator is very clear, because a metal has some finite value of the conductivity. And not to be confused with superconductors, who have exactly infinite conductivity. In metal, real metal has always some little bit of disorder. So this is just a non-zero but finite value. And then at low temperatures, you always expect that the first thing that the temperature dependence of the resistivity does is the electrons start to have you start to have electron hole excitations, and they can scatter off that. So Fermi liquid theory predicts that you have this T-squared correction on top of this disorder dependent zero temperature contribution. And here you see indeed the opposite of the insulators. Now the resistivity increases as you raise the system. So an insulator, a metal is something where the resistivity derivative of the temperature is positive. And that's actually a very widely applied distinction between metals and insulators in a regime where maybe resistivities can be comparable, but you know this distinction. In systems where you can actually tune continuously, like many of the systems that Antoine already introduced, from metal to insulator, there must be, therefore, in between some kind of critical state. So exactly at the metal insulator transition, you would have something that's neither insulating nor conducting. So there must be something that's roughly constant as a function of temperature. And because you're critical, there's no energy or temperature scale or anything that you can scale it by. The only thing that theorists then can come up with is, of course, the resistivity must be something on the order of magnitude of the quantum of resistivity, which is about 26 kilo ohm. So this is actually the standard picture of what happens at a metal insulator transition. Literally, this picture comes from this book by my collaborator, Vlad Lebusovlevich and others, called Conductor Insulator Quantum Phase Transitions. So this is something that people have been thinking about. This is how metal insulator transitions work. Now let's see how this works in practice. Antoine already introduced a lot of these Moray systems, and I'm going to talk about a slightly different one today, which is ABC Trilayer Graphene. Now, graphene you all have heard of. That's a, well, it is technically an organic compound if you consider carbon as something organic, because it consists of this honeycomb lattice of carbon atoms. And in a single layer graphene, it's very well known it has this Dirac dispersion, of linear dispersion. Now, if you put two layers of graphene on top of each other, you get this nice property that they align in such a way that one sublattice of one layer is on top of the other sublattice of the other layer, and then the dispersion becomes quadratic. You can actually continue that, and even though three layers of graphene prefer to do this so-called ABA, so that the third layer is the same as the first layer, you can, by good heterostructure engineering, you can put the third layer the same way on the second layer as the second layer is on the first layer. It's called ABC, or rhombohedral trilayer graphene. And then the dispersion around the Dirac point becomes actually cubic. So that means they already have a large Van Hoff singularity of something that's extremely flat. On top of that, what you can do is you can put a substrate on it, which forms this geometric Moray patterns. What that does is you get a large, in this case, like 15 nanometers periodicity of the system, which means in reciprocal space, you have a very small Brillouin zone, So not only do you have a very flat band coming from this cubic dispersion, it also has gaps induced by this moire structure. So you have nice isolated flat bands, and you can play with that. So as Antoine already mentioned, the real game changer about these things is not only that you can tune the band structure and you can tune, that you can make all these flat bands, but that you can tune them by just doing a top and a bottom gate. That changes the electronic density, which is usually the difference between the top or the sum of the top and the bottom gate. But the difference is usually called the displacement field, which means there's an electric field between these systems, and by that you can change the electronic band structure of the system. And as a result, this typically you've seen a picture like this also in the previous talk, that you measure the resistivity and you plot it as a function of the two gates, and you see that for a fixed filling, you can get either conducting metallic states or insulating states. So for example, here, let me focus on here. If you then fix the filling, so at half filling of this flat band, you can tune the displacement field and go through something that looks like a metal-insulator transition. And that's indeed what we got. This is unpublished data from Gloria Chen in Shanghai, who was happy to share this with me, that you have very beautiful curves of the resistivity as a function of this displacement field. It looks like there's a point where all the curves inflect, exactly like how I described the metal-insulator transition should work. So if I just take the same data and plot it in a different way, you have indeed a flat curve, basically. Everything below we can call a metal, and everything above we can call insulator. So this looks like a very beautiful realization of this metal insulator picture that was in the book and it was on my first slide. So if you have a beautiful metal insulator transition, something that looks very continuous, you can look at the properties of it. So one thing you can do is on the insulating side, you can take these curves and you can plot them on an Arrhenius plot to see what is the activated behavior of the resistivity. The Arrhenius plot is nothing but on this axis, the logarithm of the resistivity, and on this axis, 1 over the temperature. Then you try to fit it to a straight line, so you get some kind of value of the gap. In this case, for this red line, I just show how I fitted it. You get some value which is small, but all the energy scales typically in these moire systems are very small, in the order of milli-electron volts. And then as a function of the displacement field, I get different gaps and something that looks continuously going to 0. And we can, as theorists, start to wonder about what this exponent actually means. But here's the problem. This is all wrong. So the problem is that I deliberately cut off here my plot, but if I now make the whole plot of the full temperature range of the data that I have, you absolutely do not see any kind of Arrhenius behavior, even though we're supposedly on the insulating side of a metal insulator transition. Rather than having you only have like a very tiny window, like only like maybe 10 Kelvin or something, and only between 12 and 20 kilo ohm in resistivity, an extremely small window where you can see Arrhenius law behavior, where you can see activated behavior of the resistivity. For most parts, there is no activated behavior at low T. It actually looks like the resistivity flattens out. So it looks like an insulator if you glance at it from a distance, but it's actually not. I will call this a fake insulator, something that looks like an insulating curve. It goes up, but if you carefully analyze it, it actually does not follow activated behavior, what you expect for a system with a gap. So what's happening here? Why does this resistivity flatten out? And the funny thing is, once you realize that a lot of these systems that they call insulators, if you carefully look at the curve, they're actually not activated at all. You see that all over the place in these moire systems. So this is actually from the first paper on twisted bilayer graphene that started this whole moire twisted revolution, where also you only get like 1 decade of resistivity where you have activated behavior, and then it flattens out. So this is upside down, right? So this is not the resistivity, but the conductance. But you can look through that. This is a later system where they have better samples, and it looks better, but still most of, for example, this curve barely is resistive and then already flattens out. It really depends on the quality of the system and on, but usually you expect that disorder shouldn't affect the insulating state. If it's insulating, it should go activated all the way up to 0 temperature. So this is in twisted bilayer graphene, but also twisted double bilayer graphene, which means a bilayer graphene and then a twist and then another bilayer graphene. They see something, okay, well, they say it's an insulator, they fit the gap, and then it suddenly flattens out at low enough temperatures, which is weird. And also, the twisted bilayer tungsten diselenite, the system that was also discussed briefly in the previous talk, you only have like 1 decade of resistivity that looks activated, and then it flattens out again. So this phenomenon of having insulators that are actually fake are everywhere. So what's happening? It would be really weird that an insulator suddenly has like some kind of leftover conduction channels or something at low temperature. So what's happening? So as a theorist, let me just go back to the simplest thing I can imagine, namely band theory. I really like strongly correlated systems, and that's something that I think most of you are interested in, but sometimes you just got to take a step back and think about, okay, what does band theory tells us? Well, yeah, the Kubo formula. In the absence of vertex corrections, and that means 2 things, that I ignore vertex corrections. That means I ignore the possibility of Anderson insulation, which is something that we might talk about later, but for now, I'm just going to sweep that under the rug. And it just means that the scattering rates are kind of renormalized with respect to the actual scattering rates, but that's just a numerical factor. That's not something that can affect this fake insulator behavior. So what goes into the Kubo formula? Well, you have the density of states as a function of momentum and energy. You have a current operator, which depends on the system and the bands you have, and the derivative of the Fermi function that tells you that low temperatures really should be close to the Fermi level. So applying this, let me apply this to a band transition. Imagine I have 2 bands, and I can tune some parameter such that they become overlapping or not. So something that, at least on the band picture, clearly goes from insulator to metal. Yes.
So basically, your statement is that you are looking something at the insulating side of the problem, where 0 is negative, right?
Yeah.
And the point you want to make is that as you go to low T, you eventually do not get down to the lowest T in activation rate.
Yeah. Yes.
But what if the actual phase are on some sort of preemption, like that you go actually to low T, you lose the insulating phase?
That could
happen to any example.
Oh yes, that could be, yes. So I will get to the MOT metal-insulator transition, because I also will talk about this molybdenum dictelluride tungsten diselenite. This is definitely one of the possibilities. I would say what happens in this ABC trilayer graphene, well, I'm not going to give away the rest of the talk. Stay tuned. It's going to be an exciting ride. But yeah, so that could be. It could be that there's some reentrant phase. But there's an even simpler explanation. And this is, there was recently this very nice essay by Igor Mazin called The Inverse Occam's Razor, where you get easier into science and nature if you have like a very elaborate explanation. And I'm pretty sure this will not get into science and nature because I'm just going to do something with Drude formula. So if you apply this to the band transition, no, I'm just going to use Kubo. Yeah. Well, variable range hopping also diverges. Yes. Well, there's a different thing. So there's the experimental question of whether you can actually cool the system, cool the electrons properly, right? But let me give you one slide before you, because there's a very simple phenomena that's I don't think has been like appreciated much. Okay, so this is something we all know. If you have a little bit of weak disorder with the scattering time, you get Drude formula, right? Everybody's on board with that. That should not be controversial. Just take the same thing and add finite temperature to it. So this is the exact solution of the same problem of the Drude that gives you Drude formula, but then at finite temperature. And as a function of this EF, which is the distance between these bands, or if it's negative, the overlap of these bands, you get these resistivity curves at finite temperature. You get not a critical curve that's constant. You get a critical curve that is a power law divergent curve, 1/T. You get on the insulator side, nice activated behavior down to the lowest temperatures. And on the metallic side of this critical curve, you get, just because the density is very low, you're very close to a metal insulator transition, you get curves that are negative in slope, but flatten out as long as you're close to the transition. Oh, sorry. That's just, you know, this is, yeah, when the bands touch.
When the bands
touch.
Yeah. And your Fermi energy is where over?
So the Fermi energy is like here in the middle. So this parameter EF is like either the gap on the insulating side, on the metal side, it's how far you are in this parabolic band. And it's just a parabolic band. So this is an extremely straightforward calculation. But what I want to point out is that you do get these curves that are, well, they are fake insulators because they're clearly on the metallic side. You clearly have a Fermi level that crosses a band, but the resistivity goes up if you cool the system, and it for a while looks like it becomes insulating, but then it flattens out. So this is a very natural thing that happens if you just do a Drew. Simon.
When you're on the metallic side of the transition, for the ventilation, what is the asymptotic low temperature level of the resistivity?
In this case, where I ignore phonons and ignore electron-electron interactions, it is exponential small. So it's constant minus something that goes as the exponent of 1 over 10, or minus 1 over 10 should be small. But that's yeah. So I don't include any. So if you would have strong interactions, for example, close to the MOT transition, you would see a different picture. That's absolutely true, and that I will show that later.
What is it?
Oh, this is 2 dimensions. Sorry, excellent question. Yes, it's 2 dimensions just because I'm thinking about these Moray systems, and a lot of the organics also are like quasi 2-dimensional. So yeah, I really like 2 dimensions.
You're nervous about the fact that maybe the treatment of the insulators is done differently.
Yeah, so of course I'm nervous about that, and I'm nervous about the fact that at the band transition, a lot of scales go to 0, right? So in principle, exactly at the exactly at this metal insulator transitions, you should take into account that the Fermi energy goes to 0. So that has an effect on, you know, the electron-electron.
It's not particularly large.
Yeah. So you're definitely in a regime where you can't use like Boltzmann transport, but Kubo formula is kind of ignorant about that. Right? And what I yeah, exactly. Yeah, exactly. No, that's why I said I explicitly ignore vertex corrections, I ignore phonons, I ignore electron-electron interactions, but you already get this in the simplest theory. So true to Occam's razor, I just want to do the simplest theory first and see how far we can get with that.
Even though from a more rigorous point of view, you are D, if you were really treating the problem with impurity, eventually your state would be localized.
Well, if there would be no interactions, right?
This has weak localization.
No, it does not. It does not have weak localization. Yeah. But the reason I started this is in the experiments, I see less resistivity than you expect, right? So weak localization and variable range hopping is actually more resistivity than you expect. The interesting thing about this solution,
They never see weak localization.
It has not been observed. Anyway, I like that it has to be controversial. That's why that was the goal of this talk. So the exact solution that I got here has an interesting form because explicitly, analytically, you can show that it has this scaling form where the conductivity or resistivity has some temperature to the power prefactor and something which only depends on the tuning parameter EF divided by temperature. As a result, you can do the beautiful scaling where you just take the resistivity, and the procedure is you take the resistivity you have, you divide it by the resistivity at the metal insulator transition, and then the temperature you have to rescale by by this tuning parameter, how far you are away from the metal insulator transition, and you get these two beautiful branches, one branch associated with the insulator, one branch associated with the metal. So let me try to apply that to the system. So molybdenum ditellerite, I'm not going to say much about it because Antoine gave already a great introduction, even with this picture. He talked about the mod stuff, which happens at half filling, which is here F1. But because I'm talking about a band transition, let me just look at what happens at filling 2, because here there's also at full filling of the band, a band transition. You can see this in this calculation of the band structure, that the gap here just closes as a function of displacement field. So in the extended data of that Nature paper, they showed the curves there, and actually there they say this traditional picture. You have this, they say the metal insulator transition is here because there's like a constant curve. But let me just try now apply this idea that you actually, the metal insulator transition is not happening where the curve is constant. So this is the same data which Jishan was happy to share with us. And Yu Ting, the student of LAD who was working with me, she did a different thing. She just extrapolated the conductivity down to 0 temperature and see when does it go to 0. So it goes to 0 continuously as a function of the displacement field. And you can calculate the gap. You can scale this, you can find the activation gap on the insulating side. And this also goes to 0 at the same point. And at that same point, the critical curve is actually, again, something that goes as 1/T. It's not the constant one. So you again have a regime where before people would think, oh, this belongs to the insulator, but if you correctly identify the critical curve as the one that diverges as a power law, it's actually on the metallic side of the transition, so the fake insulator. And as you can say, always when you have a metal insulator or when you have any type of continuous transition, you want to see scaling. So indeed, you can do that. So this is the critical curve again. It goes as 1/T. You scale the resistivity divided by the critical curve, and the temperature divided by the energy scale, which actually scales linearly with the displacement field. Yes. Oh yeah, totally. Yeah, no, these guys are totally insulators. Yeah. No, I'm not saying there's no insulators in the world. I'm just saying that if you misattribute where the critical point is, you'll have a part where it looks like it's insulating, but it's actually.
And so in the what we call the insulator regime, the low temperature, again, the low temperature because of the resistivity is drawn out, minus something.
Minus something, yes.
Which is, and the something varies with which power.
So that then it comes to answer that question precisely, you have to take into account more things. So in this paper, so in this paper by Vlad and Yuting and Henry, they consider the effect of phonons in this situation. And there they say, because you're very close to like 0 density, the effect of phonons is a linear one because you're effectively at high temperature, small kf. And there it's the linear contribution changes sign around here. So here you have like linear up, here you have linear down. Oh, and my simple formula, it's this exponential, because then I don't have phonons and everything. It's something that's constant minus something that goes as the e to the minus to the power minus 1/T. So it's a really small contribution. So this is, I thought this is pretty cool that you kind of rethink what it means to have a metal insulator transition, even though it's just a band transition without much interactions going around. Now, the moment I go back to this ABC trilayer graphene, there the these insulating looking like curves that we saw, they are at half filling of a flat band. So then, without interactions, half filling a band always means it has to be conducting. So there's no way we can get something that looks like a metal insulator transition. So if you want to have an insulator at half filling, there's two ways that you can do that. You can have a mod insulator or a mod transition, like Antoine talked about a lot. So I'm going to go again into sort of easier, simpler solution, which is spontaneous symmetry breaking. You can either have polarization or you can have breaking of translational symmetry in order to get at half filling an insulating state.
Basically, what I have to do is to say, So I'm right at the point where the two bands are touching. I'm thermally excited states in the system, and the classical velocity of the system goes to center. And this must be ultimately what's going on there, right?
That's a good question.
Because in a classical regime, you have Fermi energy 0.
Yeah.
The temperature is always larger than the Fermi energy. And what you really is this power law is classical physics.
Yeah, I think that's a good way. I haven't thought about it, but I think that's a good way to interpret it. Yeah.
Okay. I mean, in the end, you know, you are, if you're talking about activity, it's linear.
Conductivity, yes.
So, we got if the energy, the number of states.
It's a number of carriers.
Yeah.
Yeah.
That's correct.
Yeah.
What is a Hall?
So I have not done that. So I was quite ill, and this is really like finished like last week. So
the experiments?
oh yeah, I don't know that exactly. So this is theory for these guys. I don't think they published a Hall effect around this regime. Yeah.
So you got it. The number of carriers goes like T, velocity goes like 1 over T. You have two velocities and one carrier is 1 over T. So that's the last.
Okay. Nice. Well, thanks. Yeah. No. It's like I said, it's really simple. And if you want to get an insulator or metal insulator transition half filling, the simplest thing that I like to do is always just look at ferromagnetism, and the simplest idea that you can have is imagine have some direct exchange interaction, and then what happens if you spontaneously polarize? This is, for example, the density of states of a square lattice. The up and the down spin, they both shift up. They're just a different chemical potential for the up and down spins. And Stoner-Hermite field theory just gives you a self-consistent equation to find like the actual magnetization, meaning the total number of up spins minus the total number of down spins. So this is something this is a simple Mie field theory. There's not much to it. The key point I want to make here is that the shift between the two chemical potentials is actually equal to the magnetization times the interaction strength. That's a very important point, because the moment you start to have ferromagnetic polarization in this model, you're not an insulator yet. You're completely a metal, like iron. That's a conducting ferromagnet. However, you only get insulating once this magnetization times interaction strength is equal to the complete bandwidth of the system, because then the up and down spins are only pushed away far enough. So the metal insulator transition actually, as a function of interaction strength, you have the magnetization happens when this chemical potential shift is equal to the bandwidth, and then you go, it's a transition from like an itinerant magnet to an insulating polarized ferromagnet. And then we can just do again this Kubo formula. We drag it in because it's not that much different. And again, you get this different collection of curves where you get a critical curve that again scales as 1 over T. Actually, not much has changed. It's just the same band picture, but now adding this Mie field order parameter to it. There's nothing dynamic or interaction going on, and there's a metallic region that looks like it has a fake insulator, and there is there's scaling again. So now let's go back to the ABC trilayer graphene. Why? Because ABC trilayer graphene is known to be ferromagnetic. This is a result from a paper from a year before from the Andrea Young's group, where they say rhombohedral, that means ABC, trilayer graphene drives spontaneous ferromagnetic polarization. So the problem is, if I now go look in the data for a curve that diverges as 1 over D, I didn't find it. So if a curve like that would look like this, all of these curves never diverge as fast as 1 over T. But then thought, well, maybe what happens is we are in a system when we tune the displacement field, we get close to this full polarization transition, but never really get there. So the hypothesis that we have is that all these curves here are actually on the metallic side of a metal insulator transition, where you go from partial polarization to full polarization. And one way to check that is you can do scaling. So we, as a function of the displacement field, have kind of the distance to the metal insulator transition, and you never get to 0.
You have 10 more minutes.
Okay. Yeah, I don't know if we can fit the discussions in 10 minutes.
Including some.
Okay. Yeah, so I think I want to make this point, and then I had some more to say about MOT, but luckily Antoine said most of the things I want to say about MOT metal insulator transitions anyway. So as you can see, we can scale these. We can scale this ABC trilayer graphene data by assuming we're close to metal insulator transition, but actually never get there. The zero temperature conductivity as a function of the scaling parameter nicely goes to zero. So indeed, it suggests there is, if we somehow would manage to make these bands flatter or the interaction stronger, there is an actual metal insulator transition, but we just never get there. Yeah, and as I mentioned, let me just briefly wrap up. The alternative would be metal insulator transitions. We've just seen in various systems. This is data from Andre, right, on a kappa system. This is in dilute two-dimensional electron gases, where you also see something that looks a lot like a metal insulator transition. And this is the data that Antoine already showed in the previous talk. The interesting thing is, in all these cases, you see a different kind of behavior, namely at high temperature, something that looks insulating, and then at low temperature, it has a nice Fermi liquid-like behavior with a resistivity maximum here. So that is something that you can actually see universally. You have some critical curve, which again diverges, but you don't have a fake insulating regime. Instead, you have this crossover regime where you have a resistivity maximum that signals the destruction of the deposit particles and shows that there's really some heavy interactions going on. And Yuting and Vlad and me, we wrote a review paper about this, which will hopefully be next week on the archive. So the nice thing about this is that both on the insulating side of the transition, you have a continuously vanishing gap. This resistivity maximum is also continuously vanishing as you approach the transition. And as a result, by scaling with these two parameters, you can get this nice resistivity scaling, all in the 2DEGs, in the organic systems. This has also been mentioned by Antoine, and this is, of course, data from Fernanda. And in the Moray systems, this is... Yes. Yeah, sorry. All these pictures are in the review paper with all the proper references. So as theories, I briefly want to say there's a couple of theories where DMFT is the one that stands out. So I'm not going to say much about that because Antoine really gave an introduction to that. There's some open problems related to what I just said about the fake insulators. There's, of course, fake insulators, where if you go to low temperatures, it looks like it's flattening out, but it's actually not because of some physical reason, but just because, as for example, this group showed this year, where they measured zinc oxide heterostructures, where they say, well, at low temperatures, it deviates from systematic behavior at higher temperatures because the electron temperature decouples from what you actually, so the temperature that you see here is not the actual temperature of the electron. So that's an experimental problem, and it's of course a theoretical problem to challenge to see which experimental data is real and which one is not. But this is a known problem that you have to take into account at low temperatures. But all the fake insulators I've shown you so far kick in at like few Kelvin, or 4 Kelvin, 10 Kelvin. So this is not something that has to do with any kind of refrigeration problem. And as I mentioned, I swept Anderson insulation under the rug. That is something that you can indeed say if there's no interactions but disordered, then at low enough density, you should just always have weak localization or complete Anderson insulation. And so far, they include phonons and electron-electron interactions, which is something which I think is useful to get a better, detailed grip on what happens. But the surprising thing is that without phonons and electron-electron interactions, you can get a lot of stuff right already in this molybdenum dichaloride, tungsten diselenide, and in the ABC trilayer graphene. So with that, I want to thank my theory collaborators, Vlad and Yuting, and I discussed this a lot with Simone as well, and the experimental data that we got from Jishan and Kim Van Mark and Gloria Shen. So as a conclusion, this traditional picture, I think, is not the correct picture, at least when thinking about band transitions. The critical resistivity should not be constant, but should be a power law, which means that close to the metal insulator transition, there's a regime where it looks like insulating, but it's actually on the metallic side, the fake insulator. And you can check this always with scaling, and MOT is different. So thank you for your attention.